Okay, we're not counting those, right?
Okay, it legitimately has to be a good.
Alright, so today we're going to just kind of reinforce the idea of tangent lines that we've been talking about, add in a little bit of vocabulary, and then talk about local linearity. It's a lot easier than what it sounds. Okay. So first, we just want to take a look at these graphs and practice sketching a tangent line. Right? Trying to get a feel for where that tangent line would be. And on a few of these points, we'll start to see where we can't draw tangent lines. Okay, so just go ahead and start doodling, right? Just trying to sketch out approximately where tangent lines would occur for each of these defined points on these graphs. Right? So I mean, you can use a sheet of paper as your straight edge, right? But just kind of say, well, this tangent line would look something like this, right? Just start sketching out those tangent lines.
Like for any point, or like just where they have the dots, like just for C and B or anywhere?
Yeah, just for A, B, and C on each of these, where they have the big dots. So one line where each of the dots are. Yeah.
She's when you talk about as a teacher's letter. Do you want to put all of them or just teachers? I was talking correct. Okay, tangent lines can't like cross over the graph, right?
At that point, no, but they may cross somewhere else. Like down here for this one, if I draw a tangent line, it's going to end up crossing this graph like way down here. That can happen, as long as it's not crossing like right in that immediate vicinity.
Wait. Does it matter what side the line is on? The tangent,
So like for figure 2, would C cross the?
or could it hit on the outside?
Yeah, it could hit on the outside. But for C,
Are they all
if I draw this tangent line,
Right there.
that's just going to actually end up being like right on the curve, right? Because the curve itself is a line. It's a linear function.
So
the same thing will be for A, right?
Right. Yeah.
So basically, the tangent line is the line, or is the
In this case, yes.
No, there's no passing. But you can probably skate by the way.
That is not true. You can teach yourself to do it.
It works. You just have to be smart enough to teach yourself.
Definitely not in
I have a 99% cross, and I have a C in order.
Sure.
How are you going to see an arm?
Hey, ours harder than
Okay. I've never talked about it.
all I know is that I didn't
Wait, did we ever have a senior meeting yesterday?
find my own business now.
No, why do we need a senior meeting?
To know what we're doing for our senior song.
Oh,
Come for this one.
that is here.
Yes. So yeah, like what does it look like is going to happen?
It's not for us. No matter, like all I can think, unless it's just a tangent line. Because I can see what see. I mean,
Right.
It's really sad.
like Christians,
I can't not work
would there not be a point tangent line? Because it's not for us. Unless it's just a really wonky line.
Well, in this case, we could actually draw a tangent line that's only going to hit the curve at one point. So that would be
Or Jacob broke his muffler.
Like,
Well,
it's not
really?
like-
It's so
yeah.
I bet you like
It's so no, he did it on purpose.
Only at a
No,
single
he's so
point.
embarrassed. He's driving to school today. He got out of his car. And
Just
he was
touches the
first
curve at that one point there.
What did he do? He said he just was at a stop sign and then when he went in, it was enough for super loud. He said there's a crack in it and he went
All right.
and checked it. He got rid of his car and it was like,
Does everybody have their tangent lines sketched out?
yes.
So
Let's see if I can do this.
on one, all of these were hopefully pretty straightforward, right? At A, we had a pretty steep positive tangent line. At B, we have a horizontal tangent line, and then at C, we've got kind of this negative tangent line that does something like that. It's steep negative, right? Then in figure 2, something a little bit weird happens at these points. We already kind of talked about it. At A and C, the tangent line actually ends up just being the line itself, because our original function is a linear function. Okay, so if I'm sketching a tangent line to a line, it's going to be that line. Okay?
That's just weird.
Now, what about at B? Right? Maybe. Right? I mean, it kind of seems like it should be a horizontal, but what if I draw something like that?
It can be that cool.
That would still only hit the curve at that one
And
point.
then
Right?
if you really want to be technical, if you walk down,
Yeah, or I could draw something like that, or I could draw something like that.
So it was supposed to be straight across.
So, what we actually say at a point like this, okay, if I have, we call this a corner, okay, where there's an abrupt change in slope, we cannot take the derivative at that point. Okay, we cannot draw a tangent line at that point because, like we just said, it could be in a whole bunch of different places. Okay, so at a point like this, at a corner, we say that we cannot take a derivative, or we would say that the derivative is undefined here. Something similar happens in our next graph, right? For both A and C, we can draw our tangent line, right? For A, we would get something like that. For C, we would get something like that, ish. But then down here at B, we can do the same thing that we did up here at this B. Right? I could draw a tangent line in a whole bunch of different places that only hits that curve at one point. It's a really similar idea to B. This thing, okay, it's kind of an even sharper corner. We just call this a cusp. Cusp. Okay? And it's the same idea. The derivative is not defined here at a cusp.
why is it called cusp?
I don't know. What was your question?
I said, why is it different than the corner? I just said, why is it cut like that? And then said, I don't know.
I don't know why it's called a cusp, but it's
I know it's like a cup.
it's slightly different than a corner. Corner is basically going to be two linear functions meeting at a point. A cusp is generally something that's even more like sharp, I guess, an even sharper change in slope. So at this point, there's no way for me to draw that would only hit the curve at one point another tangent line, right? If my curve is smooth like this, then that derivative, so as I get closer and closer from either side, right, I can see that that tangent line is going to go to 0 from both sides. If I think about drawing my tangent lines as I get closer and closer to this point, well, here, my tangent lines are actually getting steeper and steeper as I get closer and closer to that point, right? This one would be They're getting steeper and steeper to a negative value. So they're not getting closer and closer to a slope of 0. Same thing here, right? The slopes actually don't change. This one just has a steep negative slope all the way down, as does this, or this one would have a steep positive slope. Right? So they're not getting closer and closer to a slope of 0. Right? This one is, though. These are getting closer and closer to a slope of 0 from both sides. Right? Good so far? Then on this last one, again, something a little bit strange happens. We can draw our tangents at A and C. And so something like that. But then at B, my curve ends up being completely vertical. Okay. Wherever I've got a vertical tangent is another place that the derivative does not exist. Okay? So the derivative will not exist at a vertical tangent. Good.
I was thinking that vertical, that's like a blow my nose.
Thanks.
Everyone just talk quick for a minute.
Num num num.
It's so quick, you can still hear. Keep talking.
Yum, 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 yum.
It's really not that serious.
No, it comes.
Alright, so 3 different scenarios where a derivative would fail to exist, where we can't draw an actual tangent line, right? On this last one, we were able to draw a tangent line, but what's the slope of a completely vertical line?
No.
Undefined. Right? The slope of a horizontal line is 0.
DNA.
The slope of a completely vertical line is undefined.
I said I'm an idiot.
Okay, can we make a bet? If we get up to 100, you have to wear your hair down.
No, we have to 100. You have to give us these 5 bonus points. We're gonna give 100 in like 3 weeks.
I give it like 2.
I give it until the end of the semester, honestly.
Get rid of the end of the day.
So,
Alright, when we get to 100, I'll put my hair down.
Okay, but they have to be fair, like, don't just say the same.
yeah, it has to be fair.
I'm an idiot all through now. No, it has to be.
No,
It's the same thing.
it's the stupid counter. It has to be stupid.
So should I erase that one then?
No, keep that one.
I know we all do.
Okay, well now we're just contradicting ourselves. Are we doing I'm an idiot too?
I think that can be.
Laszlo, who votes yes on I'm an idiot?
AJ.
I'm going in. Think about it, I'm saying.
AJ just got overpowered by the females and felt like he had to put it in.
Crap, I'm going
Jacob isn't even getting say in this.
Jacob gets no say.
Oh.
Oh.
Alright.
He went to the school.
So, any questions on these situations where a derivative would fail to exist? So, this is just kind of an introduction to this idea. We're going to look at this a little bit more in depth, and we'll look at one other easy situation where a derivative would fail to exist.
I just want to know why it's called cuff.
It doesn't matter.
I'm curious now.
Alright, so let's get a little bit of vocab down here at the bottom. Alright? So, the first thing that we want to look at is concavity. Okay? I'm sure in science class you've talked about concave up, concave down, that kind of thing. Convex, concave, right? All those kind of vocab words. Right? If we're talking about the graph of a function, right, we say that the curve is concave up when the tangent line, excuse me, lies below the curve. Okay, so what that means, what that looks like graphically. Okay, if I've got, let's just say I've got a parabola, and I choose a point, right, and I say, well, I want to draw the tangent line. The tangent line lies below the curve. The curve is concave up at that point. Okay, and you can see visually, concave up just means the curve is facing up. Right, that piece of the curve is facing up. Okay. The curve is concave down then if the tangent line lies above the curve. Right, so if I were to just draw a negative parabola and choose a point, you can see that the tangent line lies above the curve. In this case, my entire graph is concave down. Right? Now, we can have, in some situations, curves be concave up on this interval, concave down on this interval. The concavity can change on certain curves. And we'll get into that a lot in the next chapter. Right? This is just an introduction to these terms. We then say at a turning point, okay, or any time we have a local min or max, the tangent is 0, or a horizontal line. Right, so again, if we think about a parabola, and I find that turning point, the point where the curve changes from decreasing to increasing, or increasing to decreasing, right at that point, the slope is always 0, or the tangent is horizontal. Right. Now, at a point of inflection, right, a point of inflection is where concavity changes. Right? So we would change from concave up to concave down, or concave down to concave up. So something like that, we could look at like a cubic function. Right? So we can see that over here, this piece is facing down. Over here, this piece is facing up. Right? Somewhere in here, we change from concave down to concave up. Right? So if I think about sketching out tangent lines, right, well, here it's above the curve, here it's above the curve, here it's below the curve. So it's somewhere right in here, right, where I change concavity. Right? We call that the point of inflection. Okay? So the point of inflection is where we change concavity. And so if I think about drawing a tangent line, right, we can see it's going to go right through the curve, right, at that point of inflection. Right? Here it's above the curve, here it's below the curve. Right? So we can say that the tangent is both above and below the curve. Both above and below. Okay, so then this E we already talked about, right? We said at a sharp corner or a cusp, the tangent does not exist. Right? We can't draw one tangent line. So we just say the derivative is undefined there. The tangent line does not exist. And then F, okay, at a point on a linear function, we said the tangent is that line, right? So the oh yeah, you still have your personal tissues. All right. So in the whole next chapter, we're going to look at analyzing mins and maxes and concavity in a lot of detail. Okay, but for now, we just want to start introducing those vocab ideas. So the next thing that we want to take a look at is something that we have touched on, but then we're going to get into using this for local linearity and estimating other values of the curve. All right. So we've talked about the two different forms of a line. We practiced that for a day, and we said, okay, more often than not, we're going to use point-slope form. Right. So just as a reminder, you can jot these down. The slope-intercept form of a line is y equals mx plus b. Point-slope form, y minus y1 equals m times x minus x1. Right, so if we go back to that first example, that parabola, where we sketched out equations of tangent lines, right, let's actually write out those equations. So what were my points for A, B, and C? So now, let's estimate the slope of the tangent lines that we sketched out. So for A, what does it appear approximately that the slope of that line is? 2 or 3? Something like that? 2.1?
It's between
All right, well then let's say like 2.5. If it's between 2 and 3. Okay, and again, we're just estimating. It's okay to estimate from a graph. We'll talk about, well, we know an exact way to do things like this, right? We know how to find the derivative and find the exact slope, but it's okay to estimate if we're just talking about the graph. What about at B? What's the slope at B? 0. And then what does it appear the slope at C would be? Negative 1 or 2? So like negative 1.5 maybe? So
I mean, why not?
we're just estimating. So it's, I mean,
Why
it's
not?
okay. So now how would I write the equation of the tangent line? If I have my slope, Math Excel popped up on the screen and Sharon got scared. It's like a horror movie.
What did he want?
Alright, how about for B?
We have to do. Oh yeah.
Yeah, because it's multiplying, so it basically nothing's there.
Right, so what, this one is pretty easy to simplify, right? What would the simplified version of this equation be?
Y equals 3.
Y equals 3, right? It's just a horizontal line at 3. Right. How about the last one? Here we go. Okay, so to write the equation of a line, we need the slope, we need the y-intercept. So one thing that we can do then, okay, once we have an equation of a tangent line, we can use that to estimate other values that are really, really close on our curve. Okay, so let's take our y minus y1 equals m times x minus x1 and use a little bit of calculus notation. Right? So if I want to use some of the notation we've talked about. Right? If I've got some random point, a, f of a, well, this is kind of the same thing as my x1, y1, right? And then for slope, we're using this notation, right? The derivative notation. So if I say f prime of a, that means the slope at my value of a. So that's my m value, right? So to make this look a little bit more calculus,
I don't think that.
I can write it like this. Right, this is still just the equation of the line, point slope form. Right, we're just using our notation to say, well, f prime of a, the derivative at a will get me the slope. And then I can take my given x value and plug it into my original function to get the y value. Right? What we can do then, we're going to look at an example here, is use this to estimate values that are really, really close. Okay, so again, if I think about a parabola, right, and I say, well, I want to draw the tangent line right there. I can use this line to estimate values on the parabola that are really, really close. So let's say this is at, I don't know, x equals 2. Well, if I find the equation of this line, I could estimate the value of the parabola at, say, x equals 2.1. And it would be really, really close, right? If I take the value of the line instead of the value on the parabola. It wouldn't be really, really close if, say, I chose x equals 5, though, right? Those two values would be really, really far apart. But if I look at just a value that's really, really close to that tangent line, I can use the line to estimate a value of the curve. So let's take a look at an example. We should have time to do this one. All right. We're actually going to jump all the way to example 6 here. Okay. So we've got this function, y equals the square root of x. And they give us the derivative. Right? They went through the whole process of doing f of x plus h minus f of x over h, limit as h approaches 0, and found this. Okay, so this function is the derivative of this function. Knowing that this is the derivative, how would I find the slope of this function at 9? All right, we're going to plug 9 into the derivative. So I can say f prime of 9 equals 1 over 2 times the square root of 9. Okay, so I get that my slope is 1 over 6. So now I want to write an equation. So it says local linearization. That's the exact same thing as tangent line, right? Local linearization is the exact same thing as tangent line. Okay, so it's saying write an equation for the tangent line of f at x equals 9. How would I do that? Right, so we need our y value. So we get 3, right? Not yet. We'll get there. So we know that we have the point 9, 3, right? And I know that my slope is 1/6. Now I just want to take these pieces of information and write the equation of the line. So that's just going to be y minus 3 equals 1/6 times x minus 9. Okay. Or if I want to solve this for y, right? Remember we talked about just adding that 3 over, so I can make it 1/6 times x minus 9 plus 3. Now the next part says, using this result, estimate the value for the square root of 9.1. if I'm taking a value that's really, really close to my value that I found the tangent line at, I can use this tangent line to estimate the value on the curve. I can just plug 9.1 in for x here to estimate what the value of 9.1 would be if I plugged it into my original function. Okay, that's the whole point of local linearization. Right? If I zoom in really, really close on a function, it's going to look like a straight line. It's going to be really, really close to my tangent. So I can say y here, y of 9.1 equals 1/6 times 9.1 minus 9 plus 3. So what do we get for that? You can use a calculator.
Oh.
181 over 6.
Oh, you're doing it in
My
your head, my hand. 3.01.
6.
Okay. So using our local linearization, this is our estimate of what the square root of 9.1 is. Alright? So now we're running out of time, so we're going to skip part D and jump to E. Actually, we'll do that tomorrow.
No homework?